My name is William Burke, and I'm from George Washington University. And our talk today is basically low-cost solutions for research computing hardware and maximizing value in acquisitions. And I think this is an important point because a lot of institutions or even individual researchers may not necessarily have the big spend monies to have all the computing resources that's necessary for their research. So I have a panel here of on site. I have Christopher Simmons from University of Texas at Dallas. I have Brock Paling, University of Michigan. I have Anita Swartz from University of Delaware, as well as Elizabeth Leakey from STEM Trek, Corey Fraser from Intel, and Kevin Goldstein from News Research. So one of the things I want to kind of talk about, or at least start the panel, is what is really considered low-cost solutions. So I'll open up the floor to Chris here to kind of talk about his experiences with what would be considered low-cost solutions and what they're doing at
Just talking to your chest. Did you?
Oh, yes, I did. Sorry about that.
I can just talk like this.
Oh, yeah.
I love these, right? We always come to these workshops and talk about high performance computing, supercomputing, yet we can't give a freaking talk about problems. All right, can you guys can hear me in here. Can you guys in TV land hear me?
Sounds good.
All right, so what is free, right? Let's start with that. Free is up for debate, right? We received, so at the University of Texas at Dallas, as I've talked about, we have a very close relationship with TAC, the Texas Advanced Computation Center. And when they decommissioned Stampede 1, we received as many racks as we could throw into the back of a truck for free. Now, free means the hardware was free, but we had to pay for the truck. We had to pay for the man hours to getting the system to our data center. We have to pay for power and cooling. We have to pay for people's time to put the system together. And a lot of people think that's a waste of time. They think buying an older solution that's not supported is a waste of time. And I want to talk about, for a few minutes to frame the rest of the discussion, about what's the difference between a 5-year-old computer and a computer you buy today, and what you can do with, let's say, low cost as opposed to free computing. So Stampede 1 went live in January of 2012. And it was a Sandy Bridge system, right? So Sandy Bridge is the architecture of the Intel chip. What architecture advancements have we had since then? Sandy Bridge, Ivy Bridge, Broadwell, Haswell, and then today we have Skylake. And Skylake is the latest and greatest. All right? What are the things that influence how fast a computer are? Clock speeds? 10, 15 years ago, clock speeds influenced. Right? I remember in 2000, 2001, I got my first 2 gigahertz Intel computer, right? And I was very excited. And I thought by today we'll be running at 20, 50, 100 gigahertz. How fast are the clocks the computers are running today? 2.3 to 2.8 on average, right? They sometimes overclock to 3, 3.5, depending on the number of cores you're using. So the clock speeds are about the same. So what's changed about the system? What makes the system faster? Well, cache.
Instructions per clock cycle.
There you go, instructions per clock cycle. That's the major speed influence. Are these instructions happening at the 64-bit instruction level? Has the x86 64 instruction set changed? No. What's changed? 128-bit instructions, right? MMX, 256-bit instructions, SSE, streaming SIMD extensions, SSE2, AVX, AVX2, electric boogaloo, right? We have all these instruction sets which are coming. If your users are using commercial software that are being downloaded as a binary, how often do you think they're being optimized to these latest, greatest vector instruction sets? Very rarely. How much faster is this latest, greatest commercial software going to run on a Skylake compared to a Broadware or Haswell? Not that much faster. All right, so all those statements are assuming that the calculation is CPU bound. Are all our calculations CPU bound? No, right? A lot of times our calculations are memory bandwidth bound. Is memory bandwidth increasing as fast as performance is increasing? No. Memory bandwidth is staying most the same. If you start doing parallel calculations, right, multiple nodes, are you CPU bound? Probably not. Are you memory bound? Probably not. You're probably communication bound. Has interconnects changed dramatically in the last 5-6 years? Well, Henry, you're shaking your head. But better. But I now have QFD XLR, right? I now have my latest alphabet. So my bandwidth is higher. Has my latency decreased? Look at most community scientific codes that are parallel, they're latency bound. So suddenly this free computer with a high quality interconnect, a clock speed that's very similar to the other clock speeds of our systems, and memory bandwidth very similar to current systems, seems very attractive. So what did we get? We got 20 racks of Stampede 1, and we have another 20 racks sitting in storage. So what do we do with these? Well, we set them up to be just like same module system, same file system hierarchy, and all of a sudden, we got people using the system. We went from 20% utilization to over 100% utilization and 50 to 100 jobs sitting in queue, in the way the system was architected. And by duplicating and replicating and taking inspiration from tax systems, people were able to transparently go from our system to tax systems. And more importantly, what we saw is we lowered the barrier of entry to tax systems. Our users who were scared to go to TAC first got their feet wet on our system. Then once they got comfortable in our system, they then went to TAC. So just because a system is given to you for free, or the hardware given for you free, doesn't mean it's going to be free in terms of cost, but it doesn't mean it's not worth the investment.
I'd like to open up to the folks to kind of speak on their experiences. So please introduce yourself, as well as what do you consider low-cost solutions, and what have you seen. I guess I could start off with Brock. If you're on.
Yep. Sorry, I'm muted.
No worries.
If you're getting feedback, I can put on headphones. So our experience here at the University of Michigan, where we have a very specific costing model, prevents us from doing the types of models that was just described, as well as we're at a scale that actually our people costs and support costs are actually significantly greater. Now we're just getting to the point where we're looking at retiring the era of processors that were just described. But in our specific case, we are required to pass on the electricity, data center, and labor costs to our users. And when you do that, and users are paying for something, they actually expect the best total experience. And because data centers and labor in our calculations generally represent about more than half the cost of actually operating a large-scale HPC system, it makes more sense to actually go out and buy hardware. Now, I will say that a couple of years ago, when we started being forced into this sort of model where we had to recover electricity and data center costs and labor costs, and was no longer being covered by the colleges, we actually figured out that based on historical models, it was actually most cost effective all in to replace equipment every 3 years. That's completely unheard of. No one ever actually really does that in practice, but it was actually most cost effective when you included data center capital recovery, data center maintenance, and other things to replace the systems every 3 years. Now, these are nodes, shared parallel file systems, interconnect generation, stuff like that. Those tended to be a little bit longer. But I will agree, and actually it is looking back out to 4 or 5 years is actually the most economical time to actually swap everything out when you include all costs. So it's extremely important in terms of what costs people are actually exposed to. If you have access to large quantities of high quality equipment that was early generation on the curve at the point it was retired, kind of like what was just described, you might be able to do that sort of model. If you're passing on everything else, you got to be looking at optimizing the total cost operations. So what we focused on more was actually increasing accessibility. As an institution, it was actually when we mined some of our data with, okay, how do I want to phrase this? It's cheaper for us to invest in labor to encourage people to start writing exceed allocations than it is for us to buy equipment and provide it at a full cost recovery rate. It is cheaper for us now to actually add labor than to expand data center investments as an institution and to keep our local systems more accessible for that kind of like small scale user teaching, undergraduate experiences, things like that. If you actually are one of those users, that 20% of users that consume 80% of the cycles, we're actually trying to invest into efforts about how we can get you access to other systems elsewhere to maintain those sorts of things locally because, again, we're being asked to recover all costs. We did a survey of schools, and the situation that we're in is actually very unique. I would argue right now Michigan is a place that is increasing its viability as a place to do good large-scale computational work. But this cost actually does create a lot of barriers. So this is a topic that's extremely interesting to us. We've been chipping away at this full cost recovery thing. We went to our deans and we proposed, what if we gave undergraduate research projects an opportunity to soak up spare cycles? Now everyone's like, well, we all do cycle scavenging, we do preemption, or we do condor backfill or something like that to make sure that your capital investments are all utilized. Guess what? When you're charging faculty for the electricity drawn, the marginal power cost matters to them, and they say, no, let it sit idle. I'm paying for that power. I'm not subsidizing anybody else. That is not fun. So we got a little bit, and so we picked away at it, and we got it so that we could enable undergraduate research projects to be able to do some work and create good experiences. And there is now a mobile app that was put together by our students who did a bunch of computer vision, machine learning, and data cleaning and other things of data that actually gives the high quality estimates that if you live in Flint, what's the chances and what's the relative level of lead in your water? They actually predict it. So everybody's known nationally about the crisis of the lead in the water in Flint. Students here use those free cycles to actually do that. And we actually hold that up as an example that, like, look, if we lower this barrier, this is actually important. I highly do not recommend doing what Michigan is currently doing, and we're fighting very hard to try to move away from that to increase the opportunities. A lot of lost opportunity costs here. We create a bifurcation between the haves and the have-nots. So that's basically where we sit for computing. In this world of full cost recovery, actually the most sensitive aspect we have is actually not compute, it's actually storage. This storage with performance, Michigan is the largest public research institution in the country. We're about a $1.5 billion research budget. About half of that is broken down into our life sciences, so our health system, so our NIH dollars, as well as other sorts of life science related money. The rest, they actually care about big storage and big I/O. there is a much bigger gap between a system that takes low man hours to operate, right? A 14 petabyte storage system like we have today, and one that a faculty feels like they can buy themselves. So to give you an idea, our medical school went and looked at just sponsored accounts. This is money that is externally funded, so it could be federal, it could be foundation, but point is, it's not internal money. It's faculty spending their own dollars. We filtered out all the enterprise class storage vendors, so Dell, EMC, NetApp, Isilon, Panasas, we filtered them all out. And then we filtered out all storage devices that were less than a terabyte. From just sponsored accounts alone, faculty were spending in excess of $1 million a year on storage devices. The medical school's research storage service at the time, which was 100% recharge based, was only collecting about $300,000 a year. So faculty in 1 year alone were spending more than 3 times the amount of money buying their own equipment. Primary survey we went around to some of these people was like, well, you know, an Isilon is really expensive compared to a Synology. The largest storage vendor on our campus is Synology. Now you could argue that's a good thing or a bad thing. If you've got sensitive data, it's probably a bad thing. If you're worried about data loss, it's probably a lukewarm thing. So how do we actually address that? We started digging into stuff, and we actually came to the same conclusion. And then when the DOE Storage 2020 paper came out, actually the same thing. And Henry knows I've been picking his brain for the last couple of years, but actually recently we deployed an archive. That archive, we are in a position where we got agreement, primarily from our medical school, but other places that have interest in sensitive data and other things, to pick up the operating cost of that system. Faculty will still be exposed to a cost, but the cost is going to be for the media. This is exactly the model that Henry championed originally. So I totally defer to him as stole the idea. We literally just got it installed a couple of weeks ago, so I can't say if it's been completely successful, but in our surveys and stuff of faculty, we told them, like, look, the price of this effectively is one, going to be all up front so that you're able to preserve data between funding cycles. Because that was the second highest thing on our survey. Faculty said it was cost per bit, but then the second one was, you're forcing me to pay for monthly, because that's our school's interpretation of what used to be known as A21, CFR 200-2, how you can spend federal dollars. You have to bill monthly for a service, so people like buying something physical so they can keep their storage. And so we turned it into a laboratory supply that by the media, the institution, the schools are paying for the operating costs for the next couple of years at least. It's a kind of in a pilot type situation. But the cost is pretty much the same as an 8 terabyte USB hard drive. So we really hope that this is a way that we're going to be able to address it, but I highly doubt with the options faculty have available at small scale. And when you look at the true total cost of operating a system, including data center operating costs, people costs, security and compliance costs, we deal with a lot of HIPAA data and a lot of export control data that can't even go to national systems. That it actually does make sense to refresh your compute, but when it comes to storage, you're going to have to put in some sort of subsidy.
We've heard from folks that are at much larger institutions, and I think Elizabeth has some great exposure and experience with smaller to constrained environments. And what has been your experience working within within that type of environment?
Can you hear me all right?
Yes, definitely.
Great. I'm Elizabeth Leak, not Leaky. That was an anthropologist. But I have about 21 years of experience with public higher education. And I was the external relations coordinator for the TerraGrid project, which preceded Exceed. In 2012, I formed a nonprofit called STEMTrek. It's a 501c3 public charity, and we accept donations from usually tech companies to support scholarly travel. It is our focus, but we also plan workshops with themes. And a lot of the stakeholders that we invite to our workshops are from EPSCoR states in the United States. EPSCoR is a program founded by the National Science Foundation that helps level the playing field. These are states and territories that receive fewer grant dollars in general. I've also been an international correspondent since about 2009, and I've covered projects in sub-Saharan Africa, in Europe, and in the US. But in Africa, the HPC Ecosystems Project was largely the brainchild of Dr. Sitola, Happy Sitola, at the Center for High Performance Computing in Cape Town. And working with Dan Stanzioni at TAC, they adopted the, I think it was 27 racks of the Ranger system in 2012. And that was deployed in 8 sites originally. Since then, this Cape Town has decommissioned a fairly large system. These are all x86 class systems, so they're fairly cohesive as an ecosystem. But then the University of Cambridge in the UK also donated a system. So now there are clusters in 18 sites in 8 countries in sub-Saharan Africa. So this is a big project. I can say, as a correspondent that's covered this project closely since 2012, that there are some really good examples where they've taken a hold of the hardware. They've used it for light research and workforce development primarily. Decommissioned hardware, in my opinion, it will probably never be, and again, it's apples and oranges. If you're comparing that ecosystem to Exceed, you'll probably be disappointed. But if you're looking at it from a workforce development standpoint, considering there's only one flagship center on the continent, the biggest system is in Cape Town. So these are all little satellites and they're navigating not only infrastructures, e-infrastructures, NRENs, and places where there are no high-speed networks, but they're navigating language barriers and cultural barriers. At the same time, they're trying to bring women into the workforce, and they've done a tremendous job. Most of our workshops have between 20 and 30% female participation, but it's not been easy. And I've been a very active advocate for women in this region. But some of the cases are more successful than others. Some had more, and again, in South Africa specifically, there are haves and there are have-nots. There are institutions that have a lot of resources, just like in the United States, and there are others that have a hard time keeping the lights on. So the haves are typically the ones that are able to install it, get it running, and get it utilized with a high rate of success. There were some who left the cluster sit on a loading dock because their door wasn't big enough to get it in, and it sat in the weather literally for weeks. They had to cut the door bigger, and there were photographs of these guys trying to put, 3 guys trying to push a rack into this makeshift door. So you have to anticipate that there are going to be challenges on the other end. In 2016 in March, I was a panelist on a presentation at the ARC meeting in Urbana, and I met Andre Jacobson. Andre led the NSF-funded PROBE project that was based at Los Alamos Lab for many years. And that was a model where they used the decommissioned systems that had been in production at Los Alamos, and successfully with using high school students as labor from the region, largely Hispanic students. Over the summer, they would come in for an internship and learn how to break these big systems apart and create self-standing clusters that were then deployed into regional universities and high schools in the area. That project, from a workforce development standpoint, was so tremendously successful. They had 20% of the students who graduated from their summer program went on to become professional employees at the lab. And that's a pretty high rate of success. 40% went on to take jobs at the lab, but not in a professional capacity. So the 20% became degreed professionals. And that's pretty important. And especially when we're looking at a diversity standpoint, considering that a lot of them were Hispanic from that region. So Andre and I launched a survey of interest, and we received 78 responses. And basically developing the survey helped us frame a list of questions that we hope to develop an assessment tool. So basically, if you're a CIO or a COO, or even someone interested in forming a research computing division from scratch, you could go through this list of questions and it would help inform you through the process. The questions had to do with floor space, data center, power, network speed, accessibility, and then the science cases available to develop and establish a case for high performance computing on your campus. And that's something that we hoped. Last year was a miserable year to try to get anything off the ground. But ultimately with that, we'd like to create not only the self-driven assessment, but a pipeline for decommissions in the United States. And the challenge we have right now is that a lot of the leadership class systems are hardware sets that are not easily broken into small standalone clusters. And the Cray XE6 model specifically. And so this summer I've been spending a lot of time talking to engineers and prospective sites to see if we could get a success case using the XE6 model that others could then follow. And we're not there yet, so we're working on it. But when you consider that the next generation at TAC will be a Cray, Blue Waters is being decommissioned in May. The Beagle system at Argonne will be decommissioned in June. That's a lot of hardware that could be useful in a training capacity, and possibly research. So this is something that we're working on now. And if anybody's interested or has information that they think will help, I'd love to hear from them. Otherwise, as far as low cost options, besides using decommissioned hardware, I was at Northern Illinois University for 8 years, and IBM was very good to Northern. They donated systems, and there was no cost in the hardware, but we had to have a really good science case to justify that donation. And I would say that came from a relationship with a faculty member primarily. Otherwise, that's all I have to say about low cost or free.
Thank you, Elizabeth.
You're welcome.
I would like to call on to Corey. He's from Intel. Can you kind of describe some of the low cost or at least cost savings that, from a cooling perspective, I think that's your area of expertise?
Yeah, so Corey Frazier, working at Intel. I have a team. We do predictive analysis on cooling solutions. So basically, I'm on the technology development of the cooling technology that are used in the HPC systems to cool some of the components that the processors that will be coming out in the future. And specifically, I guess what we're working on when it comes to liquid cooling is probably more of a higher end kind of thing. So mainly what I want to, I guess, focus low costness of it all, if you want to call it that, when it comes to liquid cooling, is maybe talk a bit more abstractly about some of the things to consider when it comes to employing liquid cooling in your various systems as you're moving forward. So for anyone who doesn't know, part of the value of going to liquid when a lot of systems are air cooled still, air cooling is always going to have a place in research and in industry. Part of the value of liquid cooling is that as you get to these higher and higher power cards that are being used, and you're looking for more and more density to get more and more compute power within your rack, of course, enough air in there to actually cool this high power component, right? And so with liquid cooling, you have the ability to have that density within your compute rack, and then be able to dissipate that heat as best you can. So for liquid cooling, there are a lot of factors. One thing that's interesting about liquid cooling is, data center and what you're piping into it, and probably even where you're located with the supporting infrastructure. So if you need something that's pretty cool, for example, you need water that's maybe, I guess, W3 class, what we call it. W3 would be something around 27 C, something of that nature. But if you need something like that, excuse me, W3 is 32, W2 is 27 C, my fault. But if you need something like that, you may need, chillers or a cooling tower. And so it becomes pretty heavy on the supporting infrastructure that's needed to support liquid cooling. So one of the things to consider when you're looking at cost solutions as it pertains to liquid cooling is thinking about your entire infrastructure, thinking about the capabilities you have to bring in cooler water, and what it is that you may need to do that. Some of the other things to consider is your overall efficiency within the system. There are different measures of that efficiency, the PUE, and maybe even a more IT-focused version. But depending upon where you're counting your total energy expenditure versus your IT systems, such as servers or the actual storage racks, you're going to get different efficiency numbers out of that, right? And depending upon where you're placing your fans, that could also be a factor. When it comes to liquid cooling versus air, the initial capital cost is generally what is higher compared to a lot of air-cooled solutions. But over the long term, you're generally going to experience some better reliability because you're going to be keeping your components cooler over a long period of time. So your total cost of ownership is expected to decrease over time, but there's an initial capital barrier, which could be a challenge for some research institutions. And one of the things to consider while you're thinking of total cost of ownership, if I may take the discussion kind of in that direction and consider how much is possibly going to cost you over time, is things like the upkeep. So from a labor standpoint, it probably won't be too much different, although you may be dealing with some heavier components based on how much fluid is inside the rack, inside the fluid lines. That could be maybe a weight concern for your data center. But things like the water treatment. So that's actually going to be a big one because there's different methods in which the water can become not as efficient as it was in cooling or possibly present an issue. So if you have, say, fouling occurring, which is the building up of sediment within the fluid lines, that can cause various inefficiencies, as well as some actual mechanical issues in the actual fluid transfer throughout the entire network. You got corrosion, which is where whatever's in the water chemically is starting to react with some of the materials, excuse me, that are being used within the actual system you have. So, for example, if you have stainless steel, you probably don't want that with your water because that's probably going to cause a bad reaction. And then there are some others as well to consider, but you have to consider, you have to treat your water every so often and make sure that it's getting the right chemicals in there to prevent some of these impurity challenges. And yeah, that's pretty much all for me.
Okay, thank you. Thank you very much, Corey. Anita, I know your experience has been somewhat different. Could you start to talk about your experience with low-cost solutions, why it worked or not worked, or
Sure.
what the types of courses or research is your university.
Sure. Can you guys hear me okay? Yes? Okay. So my situation actually is very similar to Brock's. And in fact, we followed much of the same philosophy of the community cluster model that came out of Purdue. The only difference between our situation and Brock's is that we do not charge back for electricity. That is an absorbed cost from IT. So the financial shared responsibility for the cluster. So IT provides the data center, the staff, the support, the maintenance to maintain the cluster, to install software, to provide support for cluster use by the faculty members. But then it is a bought-in process by the faculty. So 50% of the cost is covered by the faculty. They're just buying specific type of nodes. Now, each of these clusters that we've had came out of a research task force group back in 2011 at the University of Delaware. So we're actually, I believe, quite new to the game. We now have 3 clusters in place based on following that idea that we would keep going back to faculty, research groups, and asking them their needs and how we should proceed on the next cluster. However, our first cluster that we put in place, we've learned some lessons from that, and we keep changing things as we moved on to the next clusters. But our philosophy really is that we wanted to encourage faculty research groups to not have their own clusters if that was possible because of pushbacks from our facilities group. Our facilities group did not want to continue asking for quotes to convert rooms and space for these small data centers to accommodate their own individual clusters. So, for example, to be able to cool and to have the right power, facilities had to go in and set the rooms up. And that obviously has a cost associated with it. Even if the department wanted to pay for it themselves, facilities would then have to make sure that they maintained those rooms. So there was a whole issue around that. So when we first, from the task force, we encouraged people, incentivize them to give them cash for clunkers, is what we were calling them. For old clusters that they were trying to maintain in their own data centers, we were asking them to consider decommissioning them and buying into the community cluster. And we made the buy-in level at such an attractive cost because of this shared financial responsibility from IT. Our first cluster, we only charged $3,500 a node. And we basically said in order to buy into the cluster, you had to have a minimum buy-in of at least 1 node. However, you would be able to take advantage of unused cycles on the cluster through our standby queue or our spillover queue or something like that. So we made that entry level such a low cost that it was attractive to people. So even smaller groups or smaller research projects could be able to buy into that and get access to the cluster. Our goal was to provide HPC resources in conjunction with our facilitation and support for national resources, but to allow people to get access to work on their applications and their science, to be able to then think about how to scale that up. And what we have found is that by having that initial cluster on campus, we were able to attract faculty, we were able to attract graduate students, we were able to increase our exceed allocations 2-3-fold over the years. Every time somebody was able to take a project and show and prove the science, and they were able to get better allocations each year following that. So that in itself was very advantageous. What we learned is over the process, we were required to have a warranty period. 5 years was for our first cluster. What we learned, okay, the last year of that particular cluster, we ended up having to just go by, we couldn't even get warranty for the nodes, let's put it that way, from the vendor. So we had to basically use spares, and we ended up getting extra nodes that we could swap out in order to guarantee that 5-year warranty for the faculty. Now, with that said, we still have the cluster up and running. We had to dismantle a few nodes a few racks from that to make space for the new cluster that we're just about ready to bring online. But we still have still running, even though it was supposed to be decommissioned and retired almost 2 years ago. We kept it up and running, and probably when we bring this next cluster up online, we'll plan over January this year, which means it would actually at this point be 3 years from the original point that we put the cluster in place. We'll leave the head node up and the Lustre storage so people can move their data to one of the other clusters. So we have the same problem. We're not nearly as big as Michigan at all, but we have lots of issues with storage as well. And so our new CIO that just came in this past December, she's really working hard to set up governance with our faculty, with our library, with other IT, distributed IT folks around campus, because basically the staff ratio that we have to really work on this support, we have a group of 3 people that do all the support at this point, and the maintenance and the systems for our HPC groups, our community, basically. So we don't have a lot of staff, so we're trying to scale that, use the lessons that we've learned. But each year we've tried to, or each cluster we've tried to improve to give increased compute, increased memory, increased storage, and then we put more parameters on the usage of the cluster. So for example, our first cluster, we only required core specification. And we learned very quickly that we were going to have to require memory. So when we released the second cluster, we said, okay, you not only have to do cores, but now you have to specify memory. And then on both of those clusters, we had this standby queue, which meant that you had to, in order to use unused cycles, you had to have a job that could finish within 8 hours or 4 hours. So from those lessons we learned, this cluster number 3, which we're just getting ready to release, will require a time constraint as well. So we've moved from cores to memory to time now. So the more that we are specifying the resources required, the better we can utilize the cluster. We also learned that 4 and 5 years was not enough time for the clusters to stay online. So this most recent cluster, we chose to go with an open compute model from Penguin, and we're using a rolling cluster design. So after the 5 years, for the first set of 5 nodes for 5 years, this first generation that we'll release, we are already starting to, we basically sold out of the capacity before we even put the cluster in production. And we allocated more than 20% of what we thought people were going to want to buy. So that's a good problem for us to have. But the turnaround time takes, there is a turnaround time with only the few people that we have supporting to be able to now basically get this cluster in and now start thinking about how we're going to say, oh, well, you can't buy in now. We ran out. So we have to get better at that. But the nice thing is that this rolling cluster model with Penguin and the open compute, the storage racks, the storage, and the nodes can be replenished after the 5 years, and we can continue to add to it with the expectation that the rack structure will remain in place and under warranty for at least 8 to 10 years. So that made our faculty happy that they knew that their students would be able to get in and have an environment, because their biggest complaint was our students cannot finish in 4 to 5 years. And that's if they're doing a 4+1, going for undergraduate to graduate program onto PhD, and they wanted to be able to have an environment that they would be able to work consistently through their education and research period. So that's kind of where the university is right now. We're still working on, we have committees and governance. All of this is relatively new for the cyber infrastructure research. We're working on building and increasing our networks. We're also working with Henry. We like the idea of the archive storage. We still have many other aspects to work out, but I feel like we've made great progress in the last 7 years to be able to offer what I consider a low-cost entry into getting HPC resources rather than people building their own clusters. That's all I have to say.
Kevin, could you share your experiences with research computing with your company? You're in industry, so we would like to hear some of the challenges or some of the things that that you apply to making research computing lower cost.
Sure. So my name is Kevin Goldstein. I'm with Neve Research. I've been in the industry of low latency HPC for the last 17, 18 years. And what we've really run across is the fact that when you're in a resource constrained environment, you're trying to get more bang for your buck. And what a lot of that means is that you have to pay attention to how you're processing information. That you need to be able to pay attention to how you build out your software in order to take advantage of the hardware that you're going to be working on. And that covers a lot of ground. That covers a lot of ground insofar as that you need to manage your state so that you can have, if you have a time constrained situation where you have to shut down after 4 hours, that you can regenerate or rebuild your state next time you're coming back up, and you don't have to replay everything from the beginning. That also means that you have to pay attention to the kinds and amounts of data that you're processing, and realizing that a lot of this data is transient, and that the state that you're going to be building has to be process state, and that you can recover that particular process state. Another thing to consider is the fact that in a resource constrained environment, a lot of these systems are going to fail. And so when you end up having a failure, a system that does fail, you can't lose all of that data. You can't lose all of that research. You can't lose all of those cycles that's been happening. So you have to figure out how to run in some kind of high availability mode. Another topic that I've heard mentioned a lot today that I've run across on several occasions is this 80-20, that 20% of the users are taking 80%, that are taking 80% of the resources. And that, you end up having to have you have to come up with very interesting solutions for those undergraduates, people doing research, or the people doing smaller research solutions. And these people in general don't put that much attention into the problem of scale. So that when you do suddenly have to go from a smaller environment to larger environments, when you do want to grow from a small grid, from a small grid into the Exceed systems, you don't have to be able to redesign your entire system, but you want to be able to migrate your data and your state over seamlessly without having to worry about data loss, without having to worry about messaging infrastructure setup, without having to worry about storage and everything else. You want to be able to put a little bit of thought into it beforehand in order to get that extra sense of security. And then the concept of data layout is very important as well. And that goes to how you build your algorithms, not just how you build your infrastructure. Because you want to spend a lot of the time that you're using for processing, you want to be processing the information that you're interested in, not running through lists and not doing file seek disks and not doing all of these mundane tasks of computing. And so that's what we found is by putting a lot of information or a lot of thought beforehand into how these software systems are going to work, you're going to be able to save yourself a lot of extra computing resources, as well as get a lot more bang for your buck. That's all for Kevin.
Thanks. So I've heard the interesting experiences from everyone, and I'd like to kind of start talking about building social networks for research computing. How one would, whether it's collaborating with other institutions or other researchers or other IT organizations within your organization. How that could lower your costs. Like, for instance, if one organization actually has a developer that may not be in your organization or sharing resources, how would one go about doing that?
I'll take it. I was like, damn, I should go to more panels. All right, you guys hear me out there in Zoom land? Maybe. Okay, there we go. We got a yes. We got a yes. All right. So, I'm fairly new to UT Dallas. I've been at UT Dallas for about 3 months now. And a research scientist on soft money, self-funded. So I didn't talk to anyone. Only thing I did was write proposals. So I can sort of speak to what my plans are at UT Dallas, as opposed to what my experience has been. So, UT Dallas has grown dramatically over the last 8 to 10 years. 10 years ago, it was a commuter school with mostly night classes for continuing education. Now, UT Dallas has been part of the UT system since the late 60s, and as such, always supported research, but that wasn't the primary focus of the university. Consequently, a lot of fiefdoms developed. That is, campus IT was providing email, and that's about it. And so anyone doing research had their graduate student or postdoc maintain their system, cheap labor and buy hardware. And over time, as their research groups grew, they became, one-stop IT shops with a couple of different people doing distributed IT throughout campus. So a lot of what I'm encountering and we're encountering at UT Dallas is how to centralize the resources to lower total cost of ownership across campus, but at the same time, not feel like we're taking over, not feel like we're eliminating jobs. So, one of the things we've done is try to reach out to these individual IT kingdoms, these fiefdoms, and try to offer them a job and bring them into the fold voluntarily. We've also, because we can offer larger systems, you get smaller buy-in per system, and PIs save money by buying into the condo system. As I mentioned, we have the Stampede 1 base cluster. The Stampede 1 base cluster is free for anyone on campus to use. We don't charge back electricity or anything. And then people can buy into the condo system and take advantage of our interconnect and our storage, which is all DDN, GPFS. So we are starting to take business from these individual groups, even though we don't want to think of it that way. We want to think of it as a way to collaborate. So I don't have many solutions right now, other than we're trying to reach out and work with these groups without having a top-down mandate that they have to work with us. So my philosophy in all of this has always just been to put my head down, ignore politics, and just do a good job. The field of dreams, build it and they will come kind of approach. But I'm being told that's not what I need to do in my job, and that I need to be more proactive and go talk to people. So at this point, I realize that outreach and politics and working with these distributed IT groups is important. I'm hoping to hear some success stories from one of the members of this panel that give me some idea of how to go about doing it.
Yeah, and that's the thing that I'd like to hear. If we can have from our panel anyone with success stories or seen from a social networking perspective. Elizabeth, I see you raising your hand.
I've embedded. Do I have some feedback? Can you hear me? says I'm muted by host. I'm getting a lot of feedback. Is that better? Can you hear me? Okay. All right, great. It's interesting. I wanted to touch on a couple of different things, but what you just described is very common. And since I left the TerraGrid project, I have been called in on no fewer than 5 projects to do exactly what you've described as an external relations assistant, an advocate. So what happens is when people that are technical in nature write grants, they tend to write for the hardware first. And then they'll say, oh, well, we need to consider the facilities and operation. But they seldom fund external relations and outreach. But without good external relations and outreach, you'll fail because you won't have established a case for continuity because you're going to need new hardware every 5 years, basically, 5 to 8. So what has happened is I've been called in, usually it's in the 18th to 20th month of a project, and that's about the time that the granting agency says, who's handling your external relations? And they say, who's handling your, nobody. So then they say, oh, Elizabeth, we'll write a short-term contract, and that seems to be my fate. But I've learned a lot, and what Brock was saying about storage, in one case, I was hired to conduct a storage survey. And we surveyed the campus, and as Brock pointed out, we found out that there was a lot of money being lost to people doing their own storage. So rather than chase them with a stick and try to recover that loss, we launched a new storage solution that met the needs of most of the users and promoted it from a security standpoint, and had very strong drivers from legal and privacy, and the CISO was very involved. And that was very successful because then it became an attrition thing as their old, they didn't want to deal with storage. As soon as they figured out what was at risk security-wise, they came to us. And that was very, very effective. I would do that again. As far as existing resources, Exceed is a tremendous resource available to all US stakeholders and their collaborators. And the federated resources are free, are at no cost to those who apply for allocations. So it's a wonderful model. We talked a little bit, Kevin and I talked a little bit about the Jetstream project, and I was hoping Matt Vaughn or someone else from Jetstream could be available. But it facilitates gateways, and gateways are extremely useful because they accommodate domain-based practitioners that use a common set of tools. Their workflows are similar, and they can meet in this environment with a dashboard, and they don't require as much hand-holding. So that's one place where you can take a lot of the long-tail customer support cases and put them on a cloud-enabled resource that you don't have to host and you don't have to support. Storage becomes a problem. And I was helping someone last week who is doing some really critical research, hydrodynamics. So how floodwaters are expected to affect everything from the property values to the spread of contaminants in a hurricane situation, as we had with Katrina. So those are obviously very important models. The university is in a flood zone. So if they host the data, there is a risk that someday it's going to be gone. So one of the things, or actually what I recommended that this person do is look at RDA, Research Data Alliance, which assembles working groups and interest groups by domain or by area of research. And in RDA, you can see who's involved, and then you can go to the Exceed allocations portal and see what their research involves. There's a brief abstract if they've got allocations on Exceed. And through that process, we were able to find some people who had access to resources that this guy wouldn't have to host. He could just use through a gateway. And then when it came to storage, when we described what it was he was doing to a guy that I know through STEM Trek, who is retired from NOAA, he was able to put him in touch with NOAA and EPA stakeholders that host storage for the type of data he's generating. These are available on Research Data Alliance. And again, Exceed, the Campus Champion Group, which Dana Brunson and Henry are both supporting, leading. That's a tremendous resource in terms of social capital, that people that are handling the same types of problems in campuses across the country. I think Marissa told me there are more than 400 champions now. So again, that's a tremendous resource and a good network of support. So everybody needs to know they're not alone, and everybody needs to know that every problem they have has been solved by someone else or is currently being solved by someone else. And even though everybody's unique, a lot of the effort has already been tackled. So use available networks. And again, RDA and Exceed are both excellent networks. That's all I have.
Any other success stories? Who wants to take a stab at it? Rock? Rita? Okay, let's move on. Next question. The amount of FTEs for research, or as far as how do you lower your costs for whether it's full-time employees, students? Has anyone had any experience with that as far as low-cost solutions to your research computing at various institutions?
So, you know, in my current job, I'm supposed to be doing science. And that's what I was hired as, a combination science facilitator, as well as spending time trying to catalyze research, write proposals, help them with software design and things of that nature. However, due to the nature of research computing, it's hard to find sysadmins who know how to do HPC out of the box. And I end up right now doing a lot of sysadmin work. Now, historically, the way I've solved this is by teaching undergraduates. And that's what I'm doing now as well. I've had a lot of really good experience with part-time employees. And in particular, I've had, over the course of my tenure doing this, 5 or so electrical engineering EE undergrads that make them really good sysadmins. It's just the sheer nature of the tinkering they like to do. And so, you know, one of the procedures that I've done and to teach undergrads is to basically reward them for their time. As we know, a lot of being a sysadmin is banging your head on the wall until you magically tunnel to the other side. Or doing a lot of crap work. There's a lot of repetitive crap work that eventually you want to make sure you script and automate, but there's still just the amount of time you have to spend. So when I'm working with a student, when I give them work that is repetitive and boring, I acknowledge that with them. I say, listen, I know this is going to stink, and I know you're not going to enjoy this. However, if you get X done, I will give you 30 minutes of my time. So 2 or 3 times a week for all my students, I give them 30 minutes or an hour of my time on my calendar, and I let them ask me anything they want, whether it be sysadmin stuff or science or applied math or software or programming, any of one of the many subjects which I think I have some expertise in. I let them ask me questions, and I try to reward them for doing things that I'm glad I'm not doing. And so by freeing up my time and documenting everything that I do as part of a sysadmin process, I try to free up my time to do research. So that's all I have there.
Anyone else? No?
Could you please repeat the topic? I can't see the fine print.
So just basically was talking about employees for research, especially for the IT, the research computing. How do you reduce that cost? As far as the repurposing strategies at your particular institutions, organizations, when repurposing older or life cycled resources, compute, storage, switches, does anyone have any strategies that your organization may utilize that type of equipment for another service they may provide?
I'd like to make a few comments if that's okay.
Okay.
Just want to make sure there's not feedback. Sounds okay now. So I guess going back on the staff, we were talking about this earlier about utilizing staff. I know right now the University of Delaware is in a whole process of evaluating all of this. And in fact, we're working with a consulting group right now to talk about research, support, and services. So I think, hopefully I'll be able to share with everybody the outcome of the consulting service. But it is, no matter what, looking at some of the EDUCAUSE reports and things like that, there's a certain level of expectation for support and services for the researchers at any institution. And usually they feel generally happy, but people who have very specific questions, sort of like I think what Chris was alluding to, or maybe even Elizabeth, as far as domain scientists and being able to have that facilitator researcher support specifically in your domain, they're probably not getting that same level that they would like on demand, quick questions, how to get them going and things like that. So in general, from a general support point of view, most of them are pretty happy, but at the master's levels, PhD research institutions, their expectations are higher to be able to have people who do have domain experts and can help them to have that lower entry into utilizing their system. So we're not there yet, and believe me, if I'm the only support person, I can't be doing all of those things. But the idea is to grow, and pretty much most of the research or the surveys come back to say that there needs to be more staff in those areas to be able to support that at that level. So with that said, I think we could utilize our graduate students better to be able to offer them projects to work on, especially if they're in that domain. They're learning about that, and there's a lot of students that are interested in HPC. It's just that it can't come from IT to fund all of those positions. And what we need to do, and what we're starting to, Rudy Eigenman just came to the University of Delaware, great guy, really working on our HPC forum, starting to communicate what they need, and then starting to look at our undergraduate and graduates to kind of set up a queue of projects and needs, and then try to align those students with projects and learning about how to support HPC. So we're in the infancy of all of this, but I think it's a really great start. We've also had requests about a Slack channel for the distributed IT people on campus that can work directly with the IT folks that are supporting the clusters and services on the cluster to be able to ask them quick questions and more live response as opposed to submitting incidents, which is what we use to track our time. And that gets back to everything else about metrics and utilizations of staff time and being able than we can possibly imagine. But if we don't have metrics to be able to show that we have too much for the number of staff that we have, it's hard to justify to say, okay, yeah, we're gonna pay for another staff person. So I think we're moving in the right direction, and I think other people probably can have better experiences, or at least share their experiences on how they're doing their staff as well. I think there's some questions that came in on the chat, and I think it would be worth us at least responding to these. Somebody asked Elizabeth about how the centralized secure storage solution got paid for, and she said the AVP of Central IT. It was scalable with buy-in from distributed partners based on the survey. We sold the basic service and let the 20% site. And then someone asked me roughly how many PIs per staff at UDEL. Roughly how many PIs per staff at UDEL, HPC staff that is. Okay, well, I will tell you that we probably have about, right now, 1,500 accounts over our two clusters, excuse me. I'm the research support person at Delaware. We just hired a student campus champion from SIU that was working under Chet Langen from, if you've heard of him, from Exceed Fellows. Sai just started with us July 16th. So he's the second person that we have now for HPC support and general support. We have one GIS consultant. She does all our on-campus maps, and she's probably not heavily into HPC, trying to learn more about that. We have one system staff person that's full-time, 50% IT and 50% designated to engineering, so he also does support specifically for engineering. And then we have one other system staff person that spends about 10% of his time and has been recently moved into strategic operations for enterprise hardware design and implementation. So we're now short on system staff again, but we don't have any per PIs designated per staff at UD. We just have to handle them all to the best that we can, and that's actually my role. I do outreach and also do all the coordination and training, try to do all the updates on the website, keep all the events together, basically try, being involved in ACI. I'm the campus champion. So obviously I'm extremely spread thin. And my goal, to be perfectly honest with you, over the last 7 years is to just try to keep everybody happy to the best of my ability. So I'm all about customer support, client support. The customer's always right. Do whatever they can to keep them happy. It seems to work, at least in the state we are with the little staff that we have.
Thank you, Anita. Looks like we are at that 10:15 mark. So I want to thank all the panelists, and please give them a round of applause.
I guess we don't have any time for questions from the audience.
We could take one or two.
Okay, yeah, we could actually take one or two. Wasn't sure if we had a tight schedule. So, are there Are there any questions out in TV land specifically about anything that we've spoken about? Or questions to a specific panelist? Okay. Well, thank you for your time.
Thank you.
Thank you.
Thank you.
Have a good day, everybody.